Hey everybody, so we're going to get into our third lecture on dynamics today. So today we're going to be talking about types of forces, and we're going to be talking about different categories of force as well as the four fundamental forces. We'll go ahead and get started with the four fundamental forces, the first of which is the most easy to recognize, especially when you trip. So that is gravity. Gravity is the first fundamental force. The first force to be recognized. First fundamental force to be recognized. It's a field force, and it is described by the law of universal gravitation, which says that the strength of the gravitational force varies in direct proportion to the masses of the objects. So essentially, if they're big or if they're small. And inversely, to the square of the distances between them. So for the farther you get away from an object that is very, very massive, the less that it has control over you. And the closer you get to a very, very massive object, the more it has control over you. It's represented by the formula F equals a constant G, so that is constant for everywhere in the entire universe. So G is the gravitational constant. It's not the same as 9.8 meters per second squared that we learned last week. That is the constant for Earth at a particular altitude, actually. But we're not going to get into that because that makes it a little bit more complicated. But then you have the mass of the first object, the mass of the second object, over a denominator of the radius squared, or r squared. And that just means the distance between the two objects. So, if you are around a fat person, that fat person is very, very massive. There's a gravitational constant that applies equally throughout the entire universe, including to that fat person. And when the fat person comes around you, they exert a gravitational force upon you. And that gravitational force depends on how close you are to them. And because it's an inverse square law, which is fairly common in science, the closer you are to them, they get stronger and stronger and stronger. It's not just like you're getting close to them and it's proportional to how close you are to them. It's that if you move 2 feet closer, their pull on you is 4 times more. So it gets squared. If you move 4 feet closer to them, then their pull over you is now 16 times stronger. So it gets even more, exponentially more strong the closer you get to them. If you move away from them, then you're in luck because it actually gets exponentially smaller the farther you get away from them. So if you move away 2 feet, then now you're looking at a square root of 2. Less strength that they have over you than when you were at the original position. You move away more than that, now you're at fourth root of 2, and so forth. And if you can redefine that analogy with the Earth. So the Earth is extremely massive, and it's only because it's extremely massive that it actually exerts a practical gravitational force on you. Gravity is not that strong of a force. If it were stronger as you might think, then individual people could have their own gravitational fields with pebbles just flying around them. But gravity isn't that strong, so we can't. It only takes the size of like an asteroid before you can get any sort of orbit. And that's only in the absence of any planet, right? So then you have to be very, very massive to have your own orbital field. But the farther away you get from a planet, the less, an exponentially amount less of a pull that it has on you. If you get closer to the planet, it has an exponentially more strong force over you. So that's the law of universal gravitation. Weight is the effect of Earth's gravity on an object's mass, and it is a force. It is a gravitational force. And remember, force equals mass times acceleration. F equals ma. You can redefine that as the force being weight, so W equals ma. The mass would be your body mass, and then the acceleration would be the acceleration due to gravity, which is, that's right, 9.8 meters per second squared. Good job, Nick. Okay, so, or at least I'm assuming Nick gave the right answer. If you didn't, I'm disappointed in you, Nick. But anyway, so yes, it would equal W equals mg, or weight equals mass times the gravitational pull, specifically of Earth. So you all are experiencing 1g right now. G is calculated by Newton's formula, that big one that I just read out. But just having only one mass instead of two, and one can use the mass and radius of any object to calculate the gravitational field strength caused by that object. The second force we're going to talk about is not a fundamental force, it's just a category of forces. That's friction. Friction is a contact force that works against the motion of objects moving past each other. The vector for friction works opposite to the vector of movement, and the magnitude of friction is proportional to the force holding the two objects together. Friction magnitude is also dependent on the type of object that is being rubbed against, and there's something called friction coefficients. And if you get into higher level physics, you'll have to calculate what the force of friction is based on any random material's friction coefficient, which they all have been determined experimentally. We talked about this a bit yesterday, static friction. That exists between two objects that are attempting to move but are not yet in motion relative to each other. It's a sticky force that holds stuff together. So that's when you're trying to move a piece of furniture but you haven't done it yet. That initial move to get it started, the initial activation energy. Sliding friction is different. It's different when you're already pushing a piece of furniture across the floor than when you start. It takes less energy to keep it going than it does to start it moving. So sliding friction is always less than static friction. Rolling friction exists when things roll. Very, very profound. So an example would be any type of wheel. Traction is extra friction, and it's beneficial between tires and road surfaces, or like on tractors. That's why they're called tractors, because they have a high amount of traction. The next category of force we're going to talk about is centripetal force, and that's a force over a circle. It accelerates an object towards the center of a circular motion. That is what keeps the Earth in orbit and the Moon in orbit. Now moving on to the rest of the fundamental forces. These are the four forces that appear to underlie all the other known forces in nature. So they're four most important, four most basic. So we've already talked about gravity. Next we're going to talk about the strong nuclear force. We've already talked about it before when we were talking about the nuclear chemistry. And it strongly attracts at distances equal to the diameter of a proton. So it's extremely strong. In fact, it is the strongest of all the forces. And that's why physicists aren't very creative when it comes to making names, at least sometimes, because it's the strongest fundamental force, so they call it the strong force. Now, that is only at the diameter of a proton, so it's not as if it expands over a large amount of areas. The weak nuclear force is a second type of force inside of the nucleus. We have not discussed this one yet at all in the course. It's an extremely short-range force attracting at distances smaller than the radius of a proton. And it holds together the elementary particles of matter that make up protons and neutrons. And it's involved in some forms of nuclear decay, and it's about 1/1,000,000th the strength of the strong force. So if you remember back from nuclear chemistry, the strong force holds together the protons. The weak force holds together what is inside of the protons. So we're not going to get into it in this course because it's way too complex. Well, we'll talk about it at the end of the year, but it's not really going to be on your test. So the weak force holds in the stuff that's inside of the protons itself. Electromagnetic force combines electricity and magnetism because they're actually the same thing. And it exists, of course, between electrically charged particles. It can be attractive or repulsive depending on how the charges of the involved particles work. It acts over distances ranging from the subatomic to the very large. It originates in static and moving electrical charges, and it's about 1/137th of the strong force. So that's it. So go ahead now and summarize all the forces that we've talked about, and then perform section review 12C. And I'll see you tomorrow, guys. Thank you.